Okay, I'll get started with today's class. Last class, we introduced the phenomena of reflection, refraction, propagation of light and electromagnetic waves. In this class and in the next class, we're going to apply our understanding of the phenomena of propagation, reflection, refraction of light to understand, to explore images formed by mirrors and images formed by lenses. So that's the sort of overall overarching goal of this class and next Tuesday's class. Content for today's class specifically, I kind of listed it here. So I want to start with just a few general remarks about forming images with mirrors and with lenses and through reflection and through refraction. So that's the first item. The remaining items, I'm going to focus on mirrors and reflection. And we won't deal with refraction and lenses until next class. So the remaining items are, I'm going to talk about plane mirrors, that's flat mirrors, and images that they form. I'm going to talk about concave and convex mirrors, curved mirrors, and the images that they form. And we're going to look at equations that describe the formation of images by plane mirrors, convex mirrors, concave mirrors. And we're also going to look at a method called ray tracing or tracing to find the images formed by plane mirrors, convex mirrors, and concave mirrors. So the vast majority of today's class is about mirrors and reflection. The little opening part of today's class is more generally about images of objects, about reflection and refraction, and about lenses and mirrors. Okay, well, enough of that. Let's actually get on with it. Let me say what an image is. So what do I mean when I say an image? What I mean is kind of a copy, a likeness or a representation of the original thing, what we typically call the object. So the image is a copy, a likeness, a representation of an object. And in this little overhead here, I'm showing you an example. On the left, this is an image formed by reflection in a mirror. And on the right, this is an image formed by refraction in a lens. And so you can, here's this nice spherical mirror. I'd love to see this thing in real life. You're seeing an image of the trees and the sky and the ground in that mirror. So that's an example of an image of an object. Over here on the right, this is a nice lens, magnifying glass, and we're seeing an image of an eye and the surrounding face formed by refraction in this lens, in this magnifying glass. So there's just two examples of forming images of nature, forming images of humans by reflection, by refraction, with mirrors, with lenses. That's what we want to understand in today's class and understand through next class. Now, let me comment on the images a little bit, some features of the images that we're going to talk about a lot in today's class and the next class. Images can be formed both what we call upright and inverted. Now, both of these images are what we call upright. The top of the tree is at the top. The top of the eye, the eyebrow, is at the top. Those are upright images. If the top of the tree was at the bottom of the image, if the eyebrow was at the bottom of the image, that'd be an inverted image. We can form magnified and minified images, images that appear larger than the object, images that appear smaller, shrunken than the object. So we can make, with our lenses, with our mirrors, we can make what we call minified and magnified images. And then we can also make what we call virtual and real images. Both of these images are real images. For example, in the case of the mirror on the left, the light appears, the image appears to be behind the mirror's surface. But of course, it can't be behind the mirror's surface. It's just our eyes are interpreting it as behind the mirror's surface. Anyway, we're gonna over the next 2 classes talk a lot about upright inverted images, magnified minified images, and real and virtual images as ways to quantify, to describe images. So let me just mention a few keys to understanding the formation of images of objects. The first thing is that those images of objects are formed because of, due to, reflection in the case of mirrors and refraction in the case of lenses. And to understand the formation of images by mirrors and lenses, the understanding is based on the law of reflection and the law of refraction. So that's the heart, the kind of core of understanding images formed by mirrors and lenses. As I say, those images can have a variety of characteristics. They can be larger or smaller, magnified or minified. They can be upright or inverted, upright or upside down. And they can be what we call real and virtual. The equations and ray tracing methods that we'll look at in today's class and in the next class are a simple way, a simple procedure for finding the properties of the image. The kind of simple rules for finding the properties of the image. They are an approximation. So what we're going to be doing in this class, next class, is an approximation. The full understanding, the complete understanding of the characteristics, the properties of an image are actually a very, very complicated thing. They're a way too complicated thing for us to do. And it's a very complicated thing because of something called aberrations. A real image, unlike the sort of perfect images of today's class and next Tuesday's class, a real image is actually distorted a bit. It's changed a bit. That's called aberrations. Understanding aberrations is a very complicated topic. We're going to work in a world where there are no aberrations, making it a much simpler topic. Okay, so the basis, now I'm going to switch. Let me make this clear. That was all general, wordy remarks about images formed by lenses or formed by mirrors, formed by reflection or refraction. Now I'm switching. Now the rest of the class is pure mirrors. And is pure reflection. And then Tuesday's class can be pure lenses and pure refraction. Okay, so the basis of forming an image by a mirror is the law of reflection. So let's just remind ourselves of the law of reflection, because we're going to see example after example of law of reflection as we explore the world of planar, convex, concave mirrors. And of course, you know, this is a hard one to forget. It's hard to forget the law of reflection. Just try it. You just can't forget the law of reflection. Incident angle, reflected angle, measured with respect to the normal at a boundary between two media. Those two angles are equal for specular reflection. So that's the law of reflection. Theta I equals theta R. Okay, so we're going to start with plane mirrors, flat mirrors, mirrors without curvature, you know, not concave mirrors, not convex mirrors. That's our starting point. And that's like the surface of the water here. Above the surface of the water is an object, the trees in the fall. It's a nice picture. In the surface of the water, we see an image of the object. And that's an example, that's images formed by reflection. And the water's acting like a plane mirror, a flat mirror. And you can see some characteristics of the image of the object in the plane mirror. For example, the image is the same size as the object. There's no magnification or minification here. Just one thing I'm pointing out. Okay, so let's first sketch the image that's formed by a plane mirror. And this is called ray tracing. So this is our first example for plane mirror of ray tracing. And so I'm going to, on this diagram, I'm going to explain some of the terms that we use, some of the language that we use when we do ray tracing. So first of all, in the center here, this is the plane mirror, the flat mirror, the uncurved mirror. So that's standing vertically. Over here on the right, we're going to be talking about, that's the left. We're going to be talking about the object. And over here on the right, we're going to be talking about the image. But connecting those two, this line here, it runs at right angles to the surface of the plane mirror. Is what we call the optical axis. And our light rays will be traveling, you know, either parallel to the optical axis, or in ray tracing, we think of them at least traveling fairly nearly parallel to the optical axis. And I might exaggerate that, make them further away from parallel to the optical axis, but all our ray tracing rules, or our equations, formulas are going to be based on the light rays are traveling either along or nearly along the optical axis. So that's an important line. Okay, so let's go over here to the object. So this is the real tree. This is the real person. This is the real ant. That's the object. Over here on the right, this is the image. This is the image of the real tree. It's the image of the real person or the real ant. So those are the two things. And we label them with O and I for object and image. Now, we can, with ray tracing, we can reconstruct the location of the image. We can determine the location of the image and the characteristics, properties of the image by doing what we call ray tracing. We trace rays of light. We trace individual rays of light from the object to the mirror. We have them reflect off the mirror, bounce off the mirror, undergo the law of reflection, obey the law of reflection, and in that way we can figure out where the image is. And so let me show you two rays that I use to picture where the image is going to be formed. There's this one here. So this one here starts at the top of the object and heads parallel to the optical axis, strikes the mirror perpendicular to the surface of the mirror, which means it gets, according to the law of reflection, sent back along the direction in which it arrives. So that's one ray that we can picture that obeys the law of reflection. And then here's a second ray. Second ray, this one is a handy one to draw as well. This one heads off towards the center of the mirror, strikes it at some angle with respect to the normal or the optical axis, bounces off at the same angle, and emerges over here to the bottom left. So these are two rays. And you could draw many more rays, but these are two common rays that we would draw. One that traveled parallel to the optical axis, and one that traveled towards the center of the mirror. Now, our eye, so think of this as your eye, your giant eye. Well, think of this as my eye, my giant eye. Here I am. I'm going to look at the image of the object. I'm going to look at the tree image of the object tree. Now, that means I'm collecting the light rays that come from the reflection. So in comes this light ray, in comes this light ray to my eye. And what does my eye do? What does my mind do? What does my brain do? That's a good question. It figures out where these light rays from the top of the tree appear to be coming from. It traces them back to where they meet. And they appear to come from, if we trace these straight lines back, through the back of the mirror, this location here. And so we reconstruct the image of the tree as being at this location behind the mirror when the object of the tree was at this location in front of the mirror. And so that's how you use ray trace diagrams, or ray tracing, to figure out, to compute the location of the image, knowing the location of the object. Now, you might have noticed some interesting features about that image. So you might have spotted that it looked the same size as the object, and you're right. You might have spotted also it looked like it was the same distance behind the mirror as the object was in front of the mirror. You're right about that too. And what you spotted about the image, the characteristics of the image formed by the object, are the basis of some equations that we use to describe the image that's formed by an object in a plane mirror. And so that's what this slide is about. On this slide in the center here, oh gosh, there we are. In the center, I really just redrew the picture from the last slide. But I've added some labeling. I've defined some quantities that we use when describing images and objects. So let me just go through them. So for the object is over here on the left. The object distance is the distance from the center of the mirror along the optical axis. We call that P. So that represents the location of the object. The object height, that's indicated here, H. So that represents the height of the object. The image location, that's the distance of the image behind the mirror in this planar mirror. We call that Q. So that denotes the location of the image. And then H prime, that's the symbol we use for the height of the image. And so I've just added to that picture, that ray tracing diagram from the last slide, I've just added P and Q, the image and object positions, and H and H prime, the object and the image sizes. And it's in terms of those variables, that in terms of that language, that we write down equations for the properties of the image in terms of the object. And for the plane mirror, it's quite simple. Oh. Here's really the two equations. The first one says that Q equals minus P. So Q is the image position and P is the object position. And Q equals minus P says that the image is the same distance behind the mirror as the object was in front of the mirror. So we denote as positive the object location in front of the mirror. And then we denote as negative locations behind the mirror. And so the image is the same distance behind the mirror as the object is in front of the mirror, but its location is negative. Q is negative because it's behind the mirror. P was positive because the object was in front of the mirror. So that's one equation. And then the second equation is here. H prime equals plus H. That's saying that the height of the image is the same height for a planar mirror as the height of the object. And the plus sign there is saying that the image is the same way up in the planar mirror as the object. You know, the hat on the person in the image is on the top if the hat on the person in the object is on the top. The shoes on the person, object person, are on the bottom, and they'll be on the bottom in the image. So it's the same way up. It's what we call upright. And so those are this guy over here and this guy over here are the two key equations describing the image formed in a plane mirror. We talk about the magnification, which is defined as the ratio of the image height to the object height, as being +1 here. It's same size as the object, so there's no magnification. We talk about this image as being virtual because light doesn't actually come from behind mirror. It just appears to come from behind mirror. And we talk about it as upright, as I say, because the image is the same way up as the object. Okay. Oh, I want to demonstrate this. So let me share a different screen. We'll look at a little demonstration. And so in this demonstration, I'm going to show you a few little bits and pieces that go with this demonstration. I'm actually going to show you both a planar mirror and a convex mirror. But then when I actually give the demonstration of the image formation or the reflection of the mirror, we're going to just focus on the planar mirror. And then we'll return to convex and concave mirrors in this demonstration a little bit later. On the left here is a box that produces parallel rays of light. On the right here, this is a device in which I can clamp a plane mirror, or I can clamp a curved mirror. And the combination of these two devices, I can then show you the laws of reflection for curved mirrors, planar mirrors, and images formed by curved mirrors, planar mirrors, how that works. Okay, so I'm just pointing that out. There's going to be 3 rays of light that come out of that box that are parallel to one another. They'll be parallel to the optical axis. Now here's a plane mirror that I can clamp in and reflect the light off. You can see it's a plane mirror. And then I've also got which I'm going to show you later, a curve mirror. So you see the curve here. This is convex mirror. A concave mirror, sorry. I always mix those two up. Okay, so now I'm going back to the plane mirror. I'm going to clamp it into this device. And then I'm going to go and switch the lights off. Now, it actually took me a few minutes to do that because I couldn't find my way back, but I cut all that out. And now you see light directed onto the mirror and being reflected back off the mirror. But if I twist the mirror so that the light doesn't hit the mirror head on, then you see the reflection of the mirror. You see the law of reflection for the mirror. And it's those rays that allow us to form an image of an object. And so that's how images of objects get formed by a plane mirror. Let me go back to my slides. And now we've discussed plane mirrors, and so the ray tracing and the formulas for plane mirrors. Let's go on and discuss curve mirrors and the ray tracing and the formulas for curve mirrors. Okay, so here's a curve mirror, and I want to introduce a little bit of terminology. I want to introduce the radius of curvature. We give it the symbol uppercase R. And I want to introduce what we call the focal length. We give that the symbol lowercase f. And the radius of curvature, focal length, are the quantities that we use to describe this or that curved mirror. Because curved mirrors, they can be concave and convex. There's two ways of making them curved, whether the mirrored surface is on the inside or the outside. And they can also be curved a lot or just a bit. And so we need to be able to describe that. And this diagram here shows us how that works. So look at this mirror here. Here's the mirrored surface. And it forms a radius of curvature about this point that's labeled C. And so that radius of curvature is described by this quantity R. And if this was kind of a less curved mirror, then R would be bigger. If this was at a greater curvature mirror, then R would be smaller. So that's R, that's the radius of curvature. More useful for ray tracing, for optics, is actually what we call the focal length. Here's the focal length. We give that the symbol F. And the focal length is simply just, look down here, I wrote an equation for it. It's just half the radius of curvature. And so we'll use that focal length too. Now, here's an important point. So, different curvature mirrors will have different radius of curvature, would have different focal lengths. But what about the case of a convex versus a concave mirror? Concave mirrors have a positive focal length and radius of curvature. That's how we denote those, indicate those. And convex mirrors, they have a negative focal length and negative radius of curvature. So that's how we denote those. So that's how the signs of R and F distinguish convex concave, and the sizes of R and F distinguish whether your mirror is nearly planar, nearly flat, or is far from planar, far from flat. That's the language. This is the language of curved mirrors. Okay. Now, this might look a little scary, and maybe this looks like spaghetti or something like that in this diagram, but it's really not. And I think if we walk through it, I am convinced you're going to be okay with this. So this slide is about ray tracing. Remember we did it for the planar mirror? Now we're going to do ray tracing for this example of a concave mirror. And if the way I try and remember what concave is, although I still mix them up with convex, is that concave contains the word cave. And the mirror is kind of making a little cave for me to live in. So that's, you know, this is the cave of the concave mirror. Okay, so having said all that junk, let's start to explore the image that's formed by an object in a concave mirror. So we got the mirrored surface. We've got the optical axis straight through the center of the mirror and perpendicular to the mirror. And then we've got an object. It's a tree or you or me or whatever it is. And I've placed it over here on the left. I've denoted it O for object. Its position is P for the object position. And now we're going to trace the location of the image. And when we trace the location of the image, we're going to use the focal point and some rules about the focal point. And these rules about the focal point are really based on the law of reflection, that the reflected angle equals the incident angle. So let's start tracing some rays. I'm going to trace this black colored ray first. This one's maybe the simplest. It goes straight to the center of the mirror. And then it's reflected off the mirror. Reflected angle equals incident angle. And so it comes off in this direction. However many degrees above the optical axis it was, it's that number of degrees below the optical axis. So that's an easy one to draw, to picture. Now there's two more. There's a blue one and there's a green one. And I think of these two as being sisters. I'm going to clear off all this junk I've sketched over it so we can focus a little easier on the blue one and the green one. Think of them as a pair of sisters or a pair of brothers. They're a pair of sisters or a pair of brothers because in one case, you head towards the mirror along the optical axis and emerge through the focal point. In the other case, you head to the mirror through the focal point and emerge from the mirror parallel to the optical axis. So that's why I call them kind of siblings. Like all siblings, right? They've got similarities that people outside the family see, and then they've got differences that people inside the family see. I don't know whether that analogy helps or not. Anyway, let's take a look at the blue ray. This one comes in parallel to the optical axis. And the rule for mirrors is that the ray that travels in parallel to the optical axis gets reflected through the focal point. And as I say, that's based on the law of reflection, although I'm not giving you the theory of why it emerges from the law of reflection, but it does arise from applying the law of reflection. And then the other ray, the green ray, remember that one's going to head in through the focal point, and then when it bounces off the mirror, it heads parallel to the optical axis. And again, that's based on the law of reflection. That rule emerges from the law of reflection. And if you notice, all those three rays that I drew, I'll redraw just to make it even messier, the original one. that hit or struck the center of the mirror, they all cross at this location here. And this is where the image is formed. This is how we find the image. And we see that the image is closer to the mirror than the object. That's one thing you see there. You see it's turned upside down. So it's an inverted image. And also it's what we call a real image, because the light really is coming from that location. It emerges from that location. It's not just our eye thinking it comes from that location. Our giant eye over here sees the light rays come from that location. And so with ray tracing, we predicted a real inverted minified image. So it's real, meaning it's on the front face of the mirror. It's inverted, it's upside down, and it's minified. You can see it's been shrunk. And look, I'm not making this up. Here's a picture of that situation. The candle in the foreground is the object. The candle you're seeing in the mirror here, that's the image. The candle is inverted. The candle is smaller. The candle is real. The light is actually coming from a place in front of the mirror. And so that's ray tracing for a concave mirror. With that ray tracing is, again, a couple of equations that accompany the ray tracing that tell you the location and the magnification of the image. And I've written them down here. So this top equation, that's called the mirror equation. And it's relating the position of the object. So that was P. The position of the image, that's Q. And the focal length of the curved mirror, that's the focal length is half the radius of curvature. And so this is how the image and object positions are related to one another. And so we can use this to predict the location of the image, for example. And then this equation down here, so that was the first equation, it's called the magnification equation, tells you, how much bigger or smaller the image is compared to the object, and whether it's the same way or the opposite way up, whether it's upright or inverted. And that equation says that that magnification is minus Q over P. So it's the negative ratio of the image and object positions. And so those equations are how you can compute the location of the image. Like on the previous slide, we drew the ray tracing. We did the ray tracing to find the location of the image. Let me show you an example of images formed by concave mirrors. So I'm going to share a different screen now. So here we go. I hope you can see it. I'm going to jump to this one. Oh, well, it's really the same one, but I'm jumping to it anyway. And this is where we ended. This is like, we're watching some mini-series now. I've made a little mini-series about mirrors and reflection. And we watched the first episode, and it ended in this dramatic scene where we reflected the light off a planar mirror. And now we're going to learn what happens in episode 2. So I'm going to remove the planar mirror. I'm going to replace it with a concave mirror. And here we are. Here's the concave mirror. Makes a little cave for me to live in. And again, I'm going to clamp it in there as tight as I can. And then again, there was about 5 or 10 minutes where I went and turned the lights off, and I was trying to find my way back. So I edited it. And here you can see I'm back. and I'm moving the mirror. You see how the mirror converges the light. Let me just play that little bit again. You see how for a concave mirror, it bends the light rays towards the optical axis. And you actually see there, this light ray traveling parallel to the optical axis is being reflected back through the focal point. This other light ray downstairs here, parallel to the optical axis and then reflected back to the focal point. So we can see for this mirror the focal point. It's quite nice, I think. Okay, I'm going to go back to my slides. Are we getting episode 3? Yeah, you are getting episode 3. And it's coming up soon. And actually, you'll be getting episodes 4, 5, and 6 in the next class. So this is truly a 6-episode miniseries. But now that I don't know what I'm doing anymore after that, I'm going to go back and share my slides. That's what I'm trying to do. Okay. Well, that was ray tracing equations and demonstrations for concave mirror. Now let's look at ray tracing equations, demonstrations for a convex mirror. And so this slide is the ray tracing for a convex mirror. So a convex mirror, it's kind of the outer surface. Here it is. That is mirrored. And light reflects off this outer surface. Now again, to construct the image of an object, I draw an optical axis through the center of the mirror, perpendicular to the face of the mirror. I'm going to mark out the focal length of the convex mirror. Now remember that sign convention rule I discussed for differentiating convex concave mirrors. Concave mirrors, the focal length and the radius of curvature are, for concave mirrors, it's positive. And so positive is in front of the mirror. If we put the focal point in front of the mirror. For the convex mirror, the radius of curvature and the focal length are negative. So we put the radius of curvature and the focal point behind the mirror. So that's why they sit behind the mirror here. So that's a very important distinction. Then I've got the object. So this is the, oh, what did I do there? That could be the tree. I've done it again. It could be the tree, or it could be you, could be me, could be anything. And that's in front of the convex mirror. And we're interested in, again, what are we interested in? Where is the image formed? What does the image look like for the image of this tree or this person or this whatever? So again, we're going to draw several rays to find out where the image appears to be and the characteristics, the properties of the image. So one ray I'm going to draw is that first one I drew last time. It's the one, it's the easy, I think it's this is, you know, when you're kind of warming up, if you're going to exercise, you do a few little easy things, I guess. I mean, I don't know, I've never exercised. This is the sort of warming up for ray tracing. This ray, I think, it strikes the mirror at its center where the optical axis passes through the mirror, and it bounces off the mirror at the same angle that it was incident on the mirror. And so that ray looks like this here. And then there's going to be two more sister or sibling or brother rays. The one that comes in parallel and one that goes out parallel. And so let's see how we draw those. Again, as I draw those, I'm going to clear this up, get all this junk off there. So let's start with a blue ray. The blue ray comes in parallel to the optical axis, strikes the mirror, and it's going to be reflected off the mirror, and it can't pass through the focal point because the focal point's behind the mirror. Rather, it appears to have come from the focal point. That's the rule for drawing it. So it heads off in this direction. The other ray heads towards the focal point. Now, it can't reach the focal point because it's behind the mirror. It strikes the mirror. And when it bounces off parallel to the optical axis. So it heads off in this direction. So at this point, we've got three rays, the original one, the starter ray, and then the brother and sister rays. And there's a question in chat about eyeglasses. And I will postpone answering the question in chat about eyeglasses because I want to, obviously eyeglasses are not mirrors, is why I'm postponing it. But it is a good question. We're going to be talking about eyeglasses in the next class, but it would take me a little bit off tangent. And I have a personality issue where I do go off tangent easily, but I'm trying to avoid this one. Okay, so we got these three rays coming out, one at the top, two down here in the middle, and three down here at the bottom. And what does our giant eye do? A giant eye is over here. It collects these rays, and our giant eye with the giant brain and giant mind is thinking, where do the rays come from? And they appear to come from this, oops, I drew that wrong. They come from over here. It's tracing the rays back to this point here. And that point here, I'm going to have to clear this up again. That point right here is the top of the image formed by the reflection of the light from the top of the object. And so here is our image, and we've located it. We've located it, and we've found its properties. And you see here that this image is, so it's behind the mirror. So light can't really come from behind the mirror. It'd have to go through the mirror. So, it's virtual, what we call virtual. It's the same way up as the original object. The head's at the top, like the head's at the top here. So it's upright and it's smaller. So it's what we call minified. Not magnified, it's minified. And so that's the example of the ray tracing. Okay, again, this is going to happen again. So there's formulas that go with the ray tracing that allow you to predict quantitatively the properties of the image. And so this slide is kind of the partner slide to the ray tracing. It's the one with the equations. The equations for the image's location, calculating that, and the image's magnification, calculating that. So the top equation, it's again called the mirror equation. It relates the object position, image position to the focal length. And really the difference here is the equation looks the same as the concave mirror. It is the same, but the focal length will be negative here instead of positive in the concave mirror. And so that's what gives different results. This is the magnification equation, the second equation. It also looks like the same equation, right? The magnification is the negative ratio of the image to the object position. So it's the same equation, but of course the image position is different for a concave versus a convex mirror because of the different sides of the focal length. And so the magnification will be in general different. If you remember the example that we just reconstructed, we had an image that was virtual, that was upright and minified. And here is a picture of that situation. You see in the foreground the candle, you see in the background, right, the image of the candle. You see it is upright, you see it is minified, and it actually is virtual. The light isn't actually coming from that location, it just appears to come from that location. Okay, so that's the equations. And then finally, let's see a demonstration for the convex mirror. So I want to share a different screen again. And I'm going to go to episode 3. And I'm going to remove the concave mirror. And I'm going to turn it into a convex mirror. So here's a convex mirror. The mirrored side is on the outside of the cave. And I'm going to clamp that in. And then again, there was a 10-minute period where I tried to switch off the lights and find my way back home. And I cut a lot of that out, I think. Hoping I did, yeah. And here you see the light rays that are reflected. It's a little hard to see, but you can see these reflected light rays. And they are for the concave mirror. You see what it does? It diverges the light rays. It's bending the light rays away from the optical axis. And so that's, you can see why the focal length would be, or the focal point would be behind the mirror rather than in front of the mirror. These rays don't converge to a focal point on the optical axis. Rather, these rays at the top and bottom that are reflected appear to come from a focal point that's somewhere back here behind the mirror. Okay. Let me remind myself what I was going to do next. Oh, I was going to show you just a little table next. So I'm going to stop sharing this. And show you this table. So we've now talked about planar mirrors, ray tracing equations, convex, concave mirrors, ray tracing, and equations. And a easy place to get things wrong about the formation of an image from an object has to do with these sign conventions that we've been using for the formulas, the equations for finding an image from an object. And so this is a table. I just obviously, I stole it without permission from the textbook. It just is a table of the sign conventions for mirrors. And it's a table that I wanted to say, because obviously in an exam, I wouldn't expect you to, remember the sign conventions. You would get the table in the exam. Actually, in an exam now, of course, you can just have your book open and look up the table. So maybe I didn't need to show this. But look, object positions, image positions. If they're positive, they're in front of the mirror. And if they're negative, they're behind the mirror. Focal lengths, right? The focal length is behind the mirror. That's a concave mirror, convex mirror. If the focal length is positive, that's a convex mirror. It will be in front of the mirror. And magnifications, if the magnification is positive, that's an upright image. If it's negative, that's an inverted image. Okay, I got a couple of examples I want to work through, but I wanted to show you actually 2 other videos as part of my mini-series. Okay, so the this is in, chemistry physics lecture room, and on the desktop there in front of you is a concave mirror. And I'm going to walk towards it with the camera. And we're going to, we're going to look at the image of me, and we're going to look at the image of the camera as I walk towards it. And we're going to see the features of the image of me and the camera as I walk towards it. So this is going to be kind of varying the object distance. I'm going to start a long way away from the mirror compared to the focal length. And then I'm going to walk much closer to the mirror. Remember, this is a concave mirror. It's got a positive focal length. That's sitting in front of the mirror. I seem a little unsteady in this, as if I've been, I mean, I did this 8 o'clock this morning, so I wasn't drinking. So you saw an interesting thing there. Look at it as I walk back. That's an upright magnified image. And then I become a, smaller upside down image. And a concave mirror can both magnify and minify, can both invert and it can both invert and keep upright the images. Okay, now this mirror is now a convex mirror. I'm going to do the same thing with the convex mirror. Again, I'm going to just walk towards it and walk away from it, and you're going to see my image and the image of the camera. Now, in this case, I'm upright and I'm minified, and I'm going to walk closer and closer to it, and it always minifies me. I got really close to the mirror's surface there, like it was centimeters from it. And then I'm going to walk away. And so the convex mirror just seems to produce an upright image. It actually just produces a minified image. So it has quite different properties. And it's all encoded in that positive and negative focal length. Right, I'm going to go back to the slides. And I got a couple of examples and a quiz question coming up. Let's see if I can do that. So at this point, I always think, well, you really wasted a lot of time at the beginning of the lecture introducing everything. And then you actually get to the real problems and you're like racing to finish them. And I always, have regrets about that. Anyway, okay. In this particular problem, what have we got? I go get the pen working. Well, let's look at this sketch of the problem here. So this is a helicopter view of a choir and an organist. So here's the choir. They're lined up against the right-hand wall of the, I don't know, the church or the whatever. And here's the organist. He or she's sitting in front of the organ in front of the left-hand wall of the building. And we're told specifically that the organist has a mirror in front of him or her so that he can see all the choir boys over here. That mirror is 0.8 meters from the organist, and that mirror is 0.6 meters across, and that the separation of the left and right walls is 5.3 meters. And the question is, what width of the right-hand wall, or what range of the choir boys or girls can the organist see? And this is a question about planar mirrors and about images formed by planar mirrors. This is a planar mirror here. An image of the choir is formed by the planar mirror, by a reflection of the planar mirror. And the question is, you know, what's the size of that image that's formed by this particular planar mirror? And so we're going to investigate that. So this problem involves a bit of our equations or understanding of planar mirrors, and it involves a bit of geometry. And that's actually typical of these sort of ray tracing questions, problems, that they're combinations of using the equations or the ray tracing techniques for the planar or the curved mirrors, but they also always involve a bit of geometry, a little bit of geometry. Okay, so this is me solving the problem now. Solving the problem really in two steps. Firstly, I use my understanding of planar mirrors to reconstruct the image of the object, i.e. the object is the choir, and I'm making the image of the choir in the mirror. And I'm going to use the rules that we figured for planar mirrors, that the image is the same distance behind the mirror as the object is in front of the mirror, and that the image is neither magnified nor minified. It's the same size. And so let's see how that worked. Here was the mirror. Oh, gosh. Here's the mirror right in the center of this diagram. Here's the object. So this is the object, the choir, over here on the right, and the distance from the mirror to the object along the optical axis is what we call P. That's 5.3 meters. And we know that the image then for a planar mirror is formed behind the mirror at a distance Q that is the same as the object distance in magnitude. So that's Q is going to be minus 5.3 meters. So this is where the image is formed, 5.3 meters behind the mirror. And then that image, it's not going to be magnified, it's not going to be minified, it's going to be the same size. So I drew it the same size. And so that at that point, I've used my in-depth understanding, my detailed understanding of planar mirrors and the images formed of objects in planar mirrors. So that's the optical stuff. Now, to find out what region of the wall of the choir the organist can observe, I'm going to now add to this a little bit of geometry. And so let me explain the geometry I'm going to use. I'm going to use the geometry of two similar triangles. One triangle is a little one, it sits here. It's this triangle that's formed by the edge of the mirror, the center of the mirror, and the organist. And if you look at that triangle, I know the angle in it down here, I know that angle, it's the same as the angle of reflection that I pictured here. More importantly, I know the height and the width of that triangle, the vertical and adjacent horizontal sides of that triangle. They're 0.3 meters, is half the width of the mirror, and they're 0.8 meters. That's the distance of the organist from the center of the mirror. And so there's that triangle. And then the second triangle, let me draw that. It's what we call a similar triangle. So it's the same shape, has the same angles, but it's different size. It's this one here. And this one here, well, in this case, I do know the horizontal side of this triangle is 5.3 meters plus 0.8. So this is 6.1 meters. But I don't know the vertical height of that triangle. I'm just going to call it Y. And I actually want to know Y because 2Y is the range of the wall that I see in the mirror. So if I can figure out y from this geometry, then I can figure out how much of the wall the organist is seeing. And so that's where I use similar triangles. In similar triangles, as I say, similar triangles mean the angles in the corners are the same, but the overall sizes are different. So they may have been blown up or shrunken down. Similar triangles, the ratios of the lengths of sides are the same. So I'm going to consider in this small triangle, the opposite to the adjacent, and in the big triangle, the opposite to the adjacent. That is the vertical to the horizontal, and the vertical to the horizontal. So for the small triangle, the vertical is 0.3 meters, the horizontal is 0.8 meters. For the big triangle, the vertical is the unknown y, the horizontal is the 6.1 meters. Well, if you look at this, right, I can solve it for y. Y is 2.3 meters. And if y is 2.3 meters, then the width of the wall, or the width of the choir that I can see, is twice that, is 4.6 meters. And so that's the solution to that problem. By understanding how planar mirror works, by understanding the image of an object formed in a planar mirror, we've been able to say how much of the choir, how much of the wall can the organist see, based on that understanding of reflection in a planar mirror and a little bit of geometry of similar triangles. Okay, quiz question. Okay, I think that's time up, or about time up. So let me just answer that question. I think that most of you got it, so that's good. So again, the question is, what is the magnification for this planar mirror? How much is the image of the choir magnified compared to the original object of the choir? And for planar mirrors, the magnification is 1. Magnification is +1, meaning the image in a planar mirror always appears to be the same size as the object in front of the planar mirror, and it appears the same way up. It's always upright. And that's true of planar mirrors. You always get a unmagnified or unminified image, but when you have curved mirrors, convex, concave mirrors, in general, you can get magnification or minification that depends on where you position or place the object. Okay, so let's take a look at this example as our last example. So in this particular problem, we're told that a dentist uses a spherical mirror to examine a tooth. The tooth, which is going to be the object, is 1.25 centimeters in front of the mirror, and the image is 10.5 centimeters behind the mirror. So actually this one, we're told the image and the object position. So you might think, well, what am I going to have to do? This is going to be easy. Well, we're going to ask you to figure something out, actually, firstly, about the lens itself, about the, I'm doing it, now, about the mirror itself. So we're going to figure out the focal length and the radius of curvature of the mirror. And we can do that because we actually know both the object and image positions. This, I have a pet fear of dentists, and this this question brings that up, but I'm going to push on anyway and just think of it as a physics problem. So let's solve this. So part A asks us to figure out the radius of curvature. And so that made me think, well, I'm going to figure out the focal length, and then I'm going to find the radius of curvature just by multiplying the focal length by 2. And I'm going to find out the focal length from the mirror equation. That's the relationship between the position of the image, object, and the focal length. And looking at that equation, obviously, I know the image and object positions, P and Q. I don't know the focal length, so I can figure that out. So I plugged in 1 over the focal length is the sum of 1 over the image and object positions. I plugged in the image and object positions. I have to be careful, this is where it's easy to make mistakes, about the signs of these quantities. The object is in front of the mirror. The image is formed behind the mirror. So I had to plug those in. And I end up with, well, here's the inverse of the focal length when I add these two terms together, remembering there's a minus sign in here. When I take the inverse of that to get the focal length, I get 1.4 centimeters. I get for the radius of curvature, therefore twice that, 2.8 centimeters. So that's part A. We've knocked that off. We've got the focal length and the radius of curvature. Part B asks us about the magnification. What's the magnification? Well, the magnification, we can just use the magnification equation. And interestingly, we don't actually need to use the focal length in the magnification equation. It's just determined by the image and object positions. And so the magnification equation says that the magnification is negative inverse of the ratio of the image to object positions. And so I plug them in, remembering again, object position in front of the mirror, image position behind the mirror. And I get a magnification of 8.4. And so that's an example of using the mirror equation and the magnification equation for a particular example of a, in this case, a convex mirror. If I go back to the picture, if I can do that. If I go back to the picture, so the tooth was 1.25 centimeters. Oops. The tooth was 1.25 centimeters in front of the mirror. The focal length was 1.4 centimeters, so a little bit bigger. So this is the case of when we're inside the focal length. We magnified things. We made things much larger. And if you remember when I walked towards this mirror in the little demonstration, when I walked towards the mirror, suddenly when I got inside the focal length, the image inverted, it became upright, and it became magnified. And so this is an example of that. Anyway, let me end there. Just to summarize, we spent almost all the class on reflection and images formed by mirrors. We talked about images formed by planar mirrors, the characteristics, and images formed by convex and concave mirrors and their characteristics. And then finally, we looked at a couple of examples, one of a planar mirror and one of a concave mirror.